Hey everyone. Ever wish your computer could just think faster, like way faster?
Yeah.
Today we're diving into a world where that's not just wishful thinking, it's called parallel computing. And
hmm
trust me, this isn't just about your computer squeezing out a few more frames per second in a video game or something.
It's about fundamentally changing how we solve problems with computers.
Okay, so how?
See, we're always pushing for more speed, right?
Sure.
And parallel processing, where multiple processors work together, is like unlocking a whole new gear. And the system we're looking at today, HVM2, claims to be a real game changer in that arena.
All right, so no more vague promises of faster. We're going deep on HVM2, how it works, why it matters, and what it even means for the future of how our devices uh, think, I guess you could say, our guide. Victor Talon's research paper, HVM2, a parallel evaluator for interaction combinators. Now, before you grab a dictionary, we'll break it down.
Yeah, no worries. The paper focuses on how HVM2 uses this really cool theoretical model called interaction combinators, or ICs. Imagine like little bundles of instructions, almost like digital worker bees, buzzing around and interacting with each other to get the job done.
Okay?
That's ICs in a nutshell.
So instead of lines of code that a computer plods through one by one, HVM2 is more like a choreographed dance of these little instruction bundles.
Exactly. And the way they're choreographed is what makes HVM2 unique. It uses a visual language of sorts, where programs are represented by different types of nodes. Think of them like Lego blocks. You've got your constructors that build data, duplicators that copy it, erasers that get rid of it, and they all connect and interact in this, well, it's pretty fascinating.
Okay, so these nodes are the building blocks.
Yeah.
But how does that actually make things faster? What's the secret sauce here?
It's all about breaking down tasks into tiny, independent bits that can be tackled simultaneously. Imagine a huge to-do list. HVM2 is like taking that list, dividing it into a bunch of Post-it notes, and then having a whole team tackle those notes at the same time. These Post-it notes are called redexes, tiny chunks of computation that HVM2 can hand off to different processors.
So it's like having a whole team of processors working on different parts of the problem simultaneously?
Yes.
That's brilliant.
Right. And to make sure everything runs smoothly, HVM2 uses some clever tricks. On CPUs, it uses something called task stealing. Imagine if one of your team members finishes their Post-it notes quickly, they can steal some from someone who's still swamped. This keeps all the processors busy and prevents bottlenecks.
That's some serious efficiency right there. What about GPUs? Don't they handle things a bit differently?
You're right, GPUs are like those friends who love tackling things as a group. So HVM2 uses a combination of blockwise sharing, where chunks of data are strategically distributed, and shared memory optimization to make sure everyone has access to the information they need without stepping on each other's toes.
Okay, we've got all these processors crunching numbers like crazy, but what happens to all the leftovers? The data that's no longer needed. We don't want our system to get bogged down with digital clutter, right?
Right, that's where HVM2's elegance really shines through. It has a built-in garbage collection system that's remarkably efficient.
Oh, really? So it's like HVM2 cleans up after itself as it goes.
Yeah, exactly.
Tell me more.
Remember those eraser nodes we talked about earlier?
Yeah.
They're the cleanup crew as HVM2 computes. Those erasers are hard at work identifying and getting rid of data that's no longer needed. It's like having those robotic vacuum cleaners zipping around, making sure everything stays tidy without interrupting the main action.
That's seriously cool. It sounds almost too good to be true. Are there any limitations to this system?
Well, you're right to be skeptical. Every system has its quirks, and HVM2 is no exception.
Okay, so what are some of the challenges they're facing?
Well, one thing is that HVM2 has some restrictions on duplicating certain types of data. It can't just copy and paste everything willy-nilly.
So there are limits to what those duplicator nodes can handle.
Exactly.
How does that affect things?
It means programmers have to be a bit more creative when writing code for HVM2. They can't rely on the same old tricks they might use in other languages.
That sounds like it could make things a bit tricky for developers.
Yeah.
Are there any other limitations we should be aware of?
Yeah, another one is that HVM2 currently uses something called eager evaluation. Imagine a student who rushes through all their assignments, even the optional ones, regardless of whether they'll be graded. That's eager evaluation in a nutshell.
Okay, I'm starting to see where you're going with this.
Right, it can be a bit inefficient. Other systems use lazy evaluation, where they only do the work when it's absolutely necessary. This can be a big time saver, especially for complex computations.
So HVM2 might be a bit of an overachiever in that sense,
Yeah.
always doing more than it strictly needs to.
You could say that, yeah. And it does have an impact on performance, particularly for certain tasks. There's another interesting trade-off, the paper highlights.
Lay it on me.
While HVM2 excels at parallel processing, it's not quite as optimized as traditional compilers when it comes to single-core performance. It's like having a super fast sports car that's amazing on the racetrack, but not as practical for a quick trip to the grocery store.
So it's a speed demon in the right context, but there's room for improvement on that single core front.
Got it. Precisely. And speaking of limitations, there's one more we should touch upon. Remember how we talked about all those nodes fitting into 32-bit chunks for efficiency?
Yeah, that clever memory layout you mentioned.
Well, that 32-bit architecture also limits the amount of memory HVM2 can work with.
So it's like trying to run a massive program on a device with limited RAM. It can only handle so much at once.
Exactly. And this could be a bottleneck for really data-intensive applications now. Before you think HVM2 is doomed to be held back by these limitations, there's good news.
Okay, I was just about to ask about that. What are the researchers saying?
The paper outlines some very promising avenues for improvement.
I'm all ears.
For example, they're exploring the idea of bookkeeping nodes. These could potentially remove the restrictions on data duplication, giving programmers more flexibility.
So those bookkeeping nodes would be like the organizers of the HVM2 world,
Yeah.
making sure everything can be copied and managed efficiently.
Exactly. And on the evaluation front, they're looking into implementing lazy evaluation modes to boost efficiency for certain tasks. It's like giving HVM2 the option to be more strategic about its workload.
That sounds like a game changer. So even with these current limitations, the future of HVM2 seems incredibly bright.
Absolutely. The researchers are aware of the challenges, and they're actively working on solutions. And that brings us to the most exciting part of this deep dive.
Well,
What could all of this mean for the future of computing?
okay, so we've gone under the hood with HVM2, explored its inner working.
Who really got into it?
Now for the big question, what's the impact?
Right.
What could a system like this actually change out there in the real world?
Well, that's where things get really exciting. Imagine fields like scientific computing, where researchers are grappling with these massive data sets.
Huge.
Yeah. To model climate change or develop life-saving drugs.
Important stuff.
HVM2's ability to handle parallelism so effectively could be a game changer for these researchers.
It's like giving these researchers a turbocharged microscope to analyze this whole universe of data, right?
Yeah.
Instead of squinting at blurry images, they're seeing things with crystal clear resolution.
Exactly. And it's not just about seeing the data more clearly, it's about analyzing it at speeds we could, only dream of before.
Right.
This could lead to breakthroughs at a pace we just haven't seen before.
That's incredible. What about other fields? I know artificial intelligence relies heavily on processing power.
Oh, absolutely.
Could HVM2 be a game changer there too?
Absolutely. AI, especially machine learning, thrives on parallel processing. Think about training those complex models that power everything from self-driving cars to personalized medicine.
Yeah, it's crazy.
It requires immense computational power, and HVM2 could really be the key to unlocking even greater potential in AI.
So we're talking about potentially huge implications for these really cutting-edge fields.
Yeah.
But what about the everyday user? Could this eventually trickle down to make our laptops and phones even faster?
Well, that's the ultimate goal, isn't it?
It is.
While it's still early days, it's not far-fetched to imagine HVM2's influence extending to software development in general. Imagine programming languages designed from the ground up to leverage this level of parallelism.
So instead of just making our hardware faster, we're talking about a fundamental shift in how we write software too.
Precisely. We could see a future where even everyday software runs smoother, faster, and more efficiently than we ever thought possible, and it's all because we've cracked the code on parallel processing.
It's like we're on the verge of a new era in computing, where the old limitations no longer apply and the possibilities, well, they just seem endless.
It's true. This isn't just about incremental improvements, it's a potential paradigm shift in how we think about computation itself.
This deep dive into HVM2 has been mind-blowing. It's clear that this system and the ideas behind it represent a bold step into uncharted territory. And as we wrap things up, it leaves us with a question that's both exciting and a little daunting. How will this new approach to computing reshape our technological landscape in the years to come?
It's a question worth pondering, and one that researchers will undoubtedly be exploring for years to come. One thing's for sure, the future of computing is looking more exciting and parallel than ever.
I think we can all agree on that. Thanks for joining us, everyone.